Hi, good afternoon. I'm Hansen Idden from Virginia Tech. Today I'll talk about Cylon, a fast and accurate full system emulator of CXL-SSD. This is a joint work with my co-lead author, Dongha Yoon, followed by my colleagues Jinshu, Berkay, Inceisci, and our advisor, Huaicheng and Samaychno. Let's start. Modern workloads are hitting the memory wall. On one side, we have DRAM, fast at around 100 nanoseconds, but expensive with limited capacity. On the other, we have NAND flash, cheap with multi-terabyte capacity, but really slow at tens of microseconds. CXL bridges this gap. It allows heterogeneous memory device to attach via standard load store interface. CXL-SSD specifically put SSD behind CXL with a small DRAM cache for hot data and large NAND flash for capacity. CXL-SSD promise DRAM-like programmability at storage-like cost. Here's what CXL-SSD looks like. This is Samsung CMMH, the first generation prototype. CXL exposes the device directly into the CPU's physical addresses, space as a CPU-less NUMA node. Access with ordinary load store instruction, not block I/O. A CXL controller connects to the host over PCIe Gen 5 using CXL MEM protocol. Inside the device, there are two storage tiers. First, a 48 GB DRAM cache, serving hot data at around 800 nanoseconds. And next, a 1 TB NVMe NAND flash array, serving cold data at around 40 microseconds. The controller manages movement between them. When data gets affected from DRAM, it flows right to NAND. When the controller predicts upcoming access, it prefetches right from NAND into DRAM. Two numbers tell the story: 800 nanoseconds for cache hit and 40 microseconds for cache miss. And that's 50 times gap. This makes cache management a critical challenge for CXL-SSD performance. But the design space for cache policy is broad, unsettled, and with current tools, essentially impossible to explore. The storage community relies heavily on emulators for full-stack research, especially when real hardware is scarce, opaque, or not yet available. So, what do we need from an emulator? Three things simultaneously. First, full-stack execution. It can run unmodified OS and real application Redis without code changes. Second, near bare metal speed, with sub-microsecond cache hit and no VM exit overhead on fast path. Third, flexible device modeling. It can accurately emulate DRAM cache dynamics, configurable NAND timing, and caching policies. But the problem is, there is lack of research platform that delivers all three requirements. Simulators like MQSim-CXL has no full-stack support. Gem 5 and QEMU CXL are orders of magnitude too slow, and prototypes are opaque and scarce. So what we need is an open, fast, and accurate emulator to enable CXL-SSD research. We present Cylon, a FEMU-based full-stack CXL-SSD emulator. This table compares existing approaches across 5 dimensions: validation, performance, full-stack support, transparency, and extensibility. 3 different tools like MQSim-CXL and ESF are configurable, but too slow and lack of hardware validation. QEMU, cycle-accurate simulators based on Gem 5 are impractically slow for system-level studies. And QEMU can run cache, but at 15 microseconds per access. That's too slow for cache hits. Our work, Cylon CXL-SSD emulator, is the only platform that checks all 5 boxes, validated against the real hardware, high performance, full-stack support, transparent, and extensible. And we will explain how Cylon achieves all 5. Cylon serves as a drop-in replacement for CXL-SSDs, and it exposes virtual CXL device to a virtual machine. The cache OS accesses CXL memory through the standard CXL MEM interface. And Cylon manages 2 paths. The red path, cache misses, the access triggers an EPT violation causing a trap into KVM. The request is then forwarded to FEMU, which applies accurate NAND timing, and then enforces a configurable caching policy. And FEMU then flips the EPT entry from trap to direct. So next access takes the green path. And this is the green path, cache hits. The extended page table entry points directly to the DRAM cache. The cache completes at around 100 nanoseconds with absolutely no VM exits. This hybrid design faithfully reproduced both ends of CXL-SSD performance, sub-microsecond cache hits, and tens of microseconds cache misses. Next, I will talk about Cylon hypervisor design. To achieve full-stack support and flexible device modeling, Cylon builds on FEMU, a QEMU-based SSD emulator with accurate NAND timing. However, the QEMU MMI architecture is fundamentally too slow for CXL mem semantics. This breakdown shows where the time goes. It goes through VM exit because every emulated memory is marked with MMIO. Then it goes to KVM, and then it will go to QEMU user space emulation path. And that's around 15 microseconds per access with no fast path. But a real CXL-SSD cache should complete within a few hundreds of nanoseconds. So we need to optimize QEMU to faithfully reproduce sub-microsecond cache hits and tens of microseconds of cache misses. To address this bottleneck, we developed dynamic EPT remapping, or DER, which eliminates VM exits on cache hits by toggling EPT entries between two states. Each page in CXL-SSD address space has an EPTE that exists in one of two states. When the first access is in the trap state, RWXL0, this causes an EPT violation, which exits to FEMU for NAND emulation, and this is the miss path. After the miss resolves, the EPT flips to the direct state, pointing to the DRAM cache HPA with read-write enabled. And the next access on the same page will have no VM exit at all. The cache accesses directly at DRAM speed. And the safety is maintained through per EPT locks, and only the PFN and permission bits can change. And the TLP invalidation is batched via infab only on the miss path. So a single bit flip per page eliminates all VM exit overhead on cache hits. DER enables CXL-SSD emulation at realistic latency. When a miss happens, FEMU fetches the data from NAND and fills the DRAM cache. But then, it needs to flip the EPTE from trap to direct. But here's the problem. FEMU lives in user space, while EPT lives in the kernel. So every single fill and eviction requires KVM IOCTL syscall, a full round trip from user space into KVM and back. And each crossing costs microseconds. And it even gets worse. KVM has to walk entire EPT to find the right leaf entry, because EPT pages are allocated lazily and scattered across memory. So IOCTL calls for every EPT updates make Cylon less accurate and unpredictable. To eliminate this bottleneck, Cylon pre-allocate all EPT entries in a single contiguous region at VM initialization mapped into both kernel space and FEMU user space. Before this optimization, every EPT updates required an IOCTL syscall from FEMU into the kernel, plus walk table of the EPT tree to find the right entry, and that's cost 23 microseconds per miss. And with shared EPT memory, an EPT can be addressed directly by its logical page number, LPN, the SSD address, using array-style indexing without a syscall or page table walk. The result is O1 lookup and update cost per transition. This cuts the mispath latency by 29%, down to 16 microseconds with no syscall and O1 EPT walk. The CDF shown the latency distribution, with x-axis is the latency in nanoseconds, and y-axis is the fraction of requests completed within that latency. And we run MIO sequential read with 8 GB working set against a 4.8 GB cache, so both hits and misses occur. QEMU in green shows a single mode stuck at 14.6 microseconds. It has no fast path, so it cannot distinguish between hits from misses. Cylon in orange shows a clear bimodal distribution, with sub-microsecond cache hits averaging at 900 nanoseconds and microsecond scale misses. This is exactly what real CXL-SSD hardware produces. And Cylon is the first emulator to reproduce realistic CXL-SSD latency distribution. We validated Cylon against Samsung's CMMH prototype using Intel memory latency checker bandwidth test, with working set size normalized to the DRAM cache. The x-axis in the graph shows the normalized working set size compared to the DRAM size, and the y-axis in the bandwidth. Both systems shows the same two-pass behavior. Phase 1, when the working set fits in cache, Cylon sustained about 32 GB per second at remote NUMA speed. Phase 2, once the working set exceeds the cache, bandwidth drops sharply to non-bound throughput, and both converge to the same level. CMMH here drops a bit earlier due to opaque FPGA controller overhead, but the fundamental transition is still the same. Cylon can reproduce the fundamental DRAM to NAND transition. Next, I will talk about the extensibility part of Cylon. Given the 50 times gap between hits and misses, the cache policy is the #1 performance lever. CXL-SSD employ intelligent cache eviction and prefetching policy to manage data movement between DRAM and NAND, hiding the latency gap. To this end, Cylon provides a pluggable framework for implementing, testing, and validating various caching policies. For eviction, we include FIFO, LIFO, clock, and S3 FIFO. And for prefetching, we support configurable next and with degree and stride prefetching. But the key point is, eviction and prefetching logic are modular. So Cylon enables pluggable eviction and prefetching policy to explore CXL-SSD cache management design space. The second technique is an application-level interface for cooperative caching. The insight is that application often knows their future access patterns better than the device can predict. Like a database knows which table a join will scan, and a graph engine knows which vertices will be revisited. Cylon exposes an API with commands like prefetch, pin, set policy, and query stats. For example, with query stats, application developers can query the cache status to obtain fine-grained statistics such as cache miss, cache hits, and the current resident in the DRAM. This application-level interface is implemented through a shared memory ring queue for a low latency. And Cylon enables detailed memory access behavior profiling. Next, I will talk about the evaluation part. Now for extensibility result, this is what you can't do on a real hardware. On the left side is CDF of sequential read latency under different eviction policies. The table on the right shows the hit rates directly. FIFO and clock are identical at 75% because sequential strided access gives clock no second chance of opportunities. S3 FIFO gets 80% through its frequency-aware recency tracking, but LIFO reaches 90%. LIFO wins only because it affects the most recently inserted entry, so alter hot pages stay resident on the cache. So same workload, same hardware, just policy changes can give you 50% point swing. So Cylon enables eviction policy comparison. The prefetching story is even more dramatic. The CDF on the left is sequential read latency under different n degrees prefetch distance. The table on the right sweeps the prefetch degree n from 0 to 8 using S3 FIFO as the base eviction policy. The n here represents the prefetching the next n contiguous pages. At n equals 0, no prefetch, we only hit 18%, because stride 4K has a very large stride, so individual pages can rarely reuse before eviction. But as we add prefetching, each degree progressively fills the cache with pages the workload is about to need. At n equals 8, the hit rate jumps to 86%, a 68% point improvement from a single config knob. Cylon shows increasing prefetch degree shift access from NAND to DRAM. For real application validation, we run an unmodified Redis with YCSBC, 100% reads, 1 kilobyte records at 3 working set sizes, with latency as the x-axis and the CDF for that latency on the y-axis. At the small working set size, when everything fits in the cache, Cylon serves cache hits at hundreds of nanoseconds. At medium, we get mix of hits and misses, and the gap between Cylon and CMMH narrows. At large, none dominates and both converge to the same tens to hundreds of microseconds. And the gap here between Cylon and CMMH is due to FPGA overhead in CMMH. Critically, Cylon can reproduce the key transition from cache-dominated to non-dominated performance. In summary, Cylon introduces 2 performance techniques and 2 flexibility features. Dynamic EPT remapping, or DER, which eliminate FEM exits cache hits by toggling the extended page table entries between direct and trapping state, and shared EPT memory, which gives us O1 constant time cache residency updates without syscall and page walks. We also added 2 flexibility features to enable research beyond real commodity hardware fixed black box design. First, a configurable caching framework with pluggable eviction and prefetching policies. And second one, an application level interface that lets application issue prefetch, pin, affix commands for cooperative caching. Cylon is a full system CXL-SSD emulator that faithfully reproduces sub-microsecond cache hits and tens of microsecond NAND misses while providing a flexible caching framework for systematic policy exploration. Let me bring it to 3 pillars. Cylon is fast, 92 times faster cache hits than FEMU at 0.16 microseconds, and it can run unmodified OS and application with no VM access overhead on the fast path. Second is faithful. Cylon has already validated against Samsung CMMH prototype. Bimodal latency, bandwidth trends, all match the real hardware. And third, extensible. Our configurable framework reveals dramatic gains for eviction policies, configurable prefetching, and an application API for cooperative caching. You can explore architecture that go beyond what CMMH offers. And Cylon is open source and upstream to FEMU on GitHub, and we look forward to seeing what the community builds on top of it. Thank you. I'm happy to take questions.